Hey everybody, welcome to this three-part series on the subject of simulation modeling and lean process design, or mixed model line design. And I'll have to say this is one of the most exciting topics that we've dealt with over the last 20 years, and I'm really pleased to be able to share this with you. So as we get started, let me give you a brief introduction as to what it is we're talking about. Now, simulation itself, and we're talking about computer simulation here specifically, but simulation itself is not exactly new. Pretty new, but not that new. In fact, one of the, maybe originators of simulation way back when, over 100 years ago, were the Wright brothers, believe it or not. And one of the things they wanted to do was test their wing designs for lift, and they didn't want to have to try it in the real world. That could be life-threatening at worst. So they actually designed this thing that you're probably familiar with already called a wind tunnel. As a matter of fact, slight deviation, a friend of mine in high school created a wind tunnel for a science project, and it worked great. It had streams of smoke being pulled through this kind of a box with a little window with a vacuum cleaner on one side providing the suction, and on the other side, cigarettes providing the smoke. So he would light up 5 or 6 cigarettes and insert them into the little holes, and then the vacuum cleaner would suck the cigarette smoke through. Those were the days, right? Filling the science hall with cigarette smoke. Didn't seem to be a problem at the time. In any case, the wind tunnel was intended to be able to test a design without having to actually physically build it, and do some experimentation and improve the design at a much lower cost and much more quickly. And this is the same thing today we're using computer simulation modeling for, especially for our lean process designs. So what we want to be able to do is model a potential design, a value stream, if you will, to use lean speak, and perform experiments and improve the design before we physically put it into place. So the important point is that the cost of doing that, and there is a cost, is much less than putting in place a physical process, physical production line, and then having to change it or improve it later on. So an investment well worth making. So our definition of simulation modeling is building, in this case, computer models that model the behavior of an actual system or value stream or production line or manufacturing cell, and allow us to conduct experimentation in simulation time, which is much faster than elapsed time. A simulation minute might be a day or more of actual elapsed time, depending on the speed of your computer. So that's what we want to do, perform experiments. Now, the simulation model may or may not tell us the optimum design, but it certainly will allow us at a minimum to perform experiments very quickly and try different things out, and presumably end up then with a much better design before you physically make the investment of putting all this into place. So that's the goal, and that makes a lot of sense. So the wind tunnel is an example. Let me give you another one, and this is something that happened to me personally. In my early years as a lean consultant, as a lean line designer, didn't have simulation. I mean, we knew about it. I studied simulation in college and in my MBA program, but those were the days when I wouldn't say I was dealing with stacks of computer cards. It was a little bit after that, but certainly kind of dumb terminals and reams of output, no graphical output, no animation, and it was just tedious. So when I first started doing lean consulting, simulation wasn't really an option. And the software that was available was also very expensive. Still not cheap, but very expensive. So it wasn't an option. And here's the case history I wanted to share with you, just to get you inspired about the opportunities here, even in what was actually a pretty simple design. This was with a company that makes, American company that makes faucets. So bath, shower, kitchen, a lot of different models, not a lot of work. I mean, how much time does it take to assemble a faucet? Not a whole lot of time, less than 2 minutes to assemble it and put it in a box. So what could be simpler? But they had a lot of different models and a lot of different styles and a lot of different materials. So this particular design was a series of cells, assembly cells, with about 4 people per cell. So designing a cell, the takt time or the rhythm or beat of the cell was about 20 seconds, which is really pretty much too fast, but that's what we had. 20 seconds of work for each station, where you do a piece of that assembly work, and then you put it in a box. And so 20 seconds, that's about 3 per minute. If you work 400 minutes in a shift, you'd expect about 1,200, right? Do the arithmetic, 1,200 units per shift. So easy, we did everything right, padded floors, material presented optimally, good lighting, good instructions. Everything was done the best we could, best we knew how at the time. And day 1, the line started running, and we got about 850. Well, gee, I thought we designed this for 1,200. So maybe it's just a learning curve, we thought. So we'll keep on going, and people will kind of get used to it and get flowing a little bit better. So the next day was maybe 900, 920. This was, after a few days of this, we were starting to get concerned. What is going on here? And eventually we discovered that really the small variations in just people time, it really wasn't differences in the work content of different models. It was all very similar, but just small variations in people's time resulted in small delays. But when you have 1,200 potential delays in a shift, they really added up. And every time you miss one of those beats or rhythms, you're just not going to get it back. And at the end of the day, we were short. So what to do? We'd already put these physically into place. Well, there were some remedial actions that we were able to take. For example, adding more buffers in between stations helped, but we never really got to that 1,200. We got closer, much closer than we were on day 1, but didn't get there. So what's the lesson here? Well, the lesson is that even if your design's simple, the impact of variability can really have a dramatic effect on your line performance. And it's really hard, even in something as simple as that, it's really hard to understand all of the nuances of what can happen that affect line performance. And this is especially doubly, triply, quadruply important in a mixed model line design, because you're dealing with, let's count the potential variabilities. You've got just normal human variability. Sometimes people work faster and slower. Even if your standard time is 1 minute, people don't work like robots. So some people are going to be faster and slower. That impacts throughput. That's one thing. The other thing is different models have different work content. You're never going to get away from that. So that's another challenge. How do you balance that? How do you overcome those kind of issues is a second challenge. Then you've got feeder lines and options. And then you've got changes in mix that can happen on a daily basis, especially if from a lean philosophy point of view, we're trying to build to order and not build products that the customer doesn't really want. So you have all these challenges that we're dealing with, and how do you understand how that line is going to perform? It's pretty much impossible to understand that in your head. And compound that if you're not dealing with a cell, but an actual line with lots of workstations. So you have more complexity, let's say. Even if you don't have a lot of variability, if you have more complexity, that adds to it as well. So to make a long story short, years later, when I had access to simulation modeling, I took that cell at the faucet manufacturer. I remembered the design because it was so simple, and I created a model, and I ran it, and the model showed me pretty much what exactly happened. And if I'd had that model back when I was actually working on that project, we could have taken much better corrective action. We could have actually designed the line up front that would have performed to expectation and really would have achieved that 1,200. It might have involved actually adding stations, adding a 5th station, but we would have been able to have much more predictable and actually successful results and a lot less Kaizen. This word Kaizen that you're probably familiar with, Japanese for continuous improvement. Kaizen is intended to be small improvements. You shouldn't be having to Kaizen a design in any major way. That just means you didn't do it right the first time. So Kaizen is a really powerful thing, but for tweaking or fine-tuning, it shouldn't be for making major repairs to a design. So I discovered that simulation could be a really powerful tool, and it really needed to be part of my toolkit. But here's the challenge, and here's the opportunity for us. The challenge is that the software is still complicated and it's still pretty complex. When I left this original simulation lean consulting company that I joined in around the year 2000, I was so convinced that simulation modeling needed to be part of my toolkit for a line designer that I joined a simulation company, a California-based company, as their quote-unquote lean guy. And what I learned were a couple things. Number one, simulation was really powerful. And the people that were working building models were really good, much better than we were actually, at asking the right kind of questions and really drilling down to understand how a process works. They had to be able to ask those questions, because if you didn't, then the model wasn't going to reflect reality well enough. It wasn't going to be a good model. So that's one thing. But the other thing I learned was that to really get good at simulation is like getting really good at being a C++ programmer. It's not something you do in your spare time, at least at that time. You really had to put in the hours. Remember, Malcolm Gladwell wrote a book called Outliers, and this number is pretty much made up, but the number that he quoted was 10,000 hours of continually more challenging practice in any particular skill, whether it's becoming a good guitar player, or say, not good, a world-class guitar player, or a scientist, or an author, or any skill you want to name. You need 10,000 hours of continually more demanding kind of application. I don't know, 10,000 is, as I said, it's kind of a made-up number, but whatever it is, it's a lot of hours. And so I pretty quickly realized, boy, I was going to have to choose careers. Do I want to become a simulationist, or do I want to become a lean line designer using simulation as a tool? And I chose the latter, right? Stick with lean, but incorporate simulation more into my toolkit as best I could. And so we have a real breakthrough. I think a real breakthrough that happened just in the last few years that I'm going to share with you in lesson 2. But I'll cut to the chase. I'll give you a hint that building the kind of models that we're talking about building, assembly lines, sequential work, has become a lot easier because I partnered with the simulation company that I worked for over the last few years, and the smart people over there, one in particular, has developed a simulation modeling tool built in Excel that's actually a dynamic, discrete event simulation engine that doesn't do everything for everyone, but it certainly helps with designing these kind of lean processes that we're dealing with most of the time. And so I'm going to share with you how that works exactly in lesson 2, show you examples of this. So this is the exciting breakthrough that finally, I'm speaking personally here, finally I have a tool in my toolkit that I can use to incorporate simulation into my lean practice without becoming a full-time simulationist and without actually spending many thousands of dollars on the software either. I already had Excel. So that's the exciting part. I'm just kind of giving you a preview. Right? So let's continue on though with this introduction and talk about why simulation is so important in more detail. Okay, so my background, I've already told you a little bit about it, but just to recap, I started my lean journey back in the mid-90s. Actually, I took my first lean class back in 1989, and I was in the aerospace industry. I was involved with material manager, and got very excited about it, became the lean leader in my company at that time. And then in 94, decided to become a lean guy full-time, joined the company that trained me, and had a chance to work on lots of projects. And I already shared one with you. With a lot of the biggest companies in the world, frankly, like Boeing and General Electric, and a lot of smaller companies as well. So great learning experience, but again, had no simulation experience. In 2000, I joined the simulation company, the Quran Consulting Group in San Diego, California. And they were really good at building models, and I was the lean guy for a couple years until I realized I wasn't going to change careers, and left them and went back to full-time lean consulting, but with this nagging feeling that somehow I needed to get my hands on the use of simulation and be able to apply it and incorporate it into our practice in order to improve the the testing of our designs before we actually put them into place, as I've told you before. So that was it. And it was only until a few years ago that I was able to actually get my hands on and kind of resolve this issue of the learning curve and being able to actually do this. So I'm not giving away the secret quite yet in terms of what happened, but in lesson 2 of this series, I'm going to be showing you exactly what happened. So stay tuned for that. Now, some of you may be working for larger companies where simulation is an option, that you have a simulation group. Larger companies typically are doing this more and have those kind of skills available. And what we need to then decide for you as a lean person, as a manufacturing professional, is how far do you want to go down that road? And what I would suggest is, unless you're willing to really dedicate yourself to it, that you, instead of thinking about becoming a simulation expert, which is, as I said, a kind of a big commitment, that you become a super user. And so that is our focus in our training, and the direction we're going down is how do we train people to become super users in 2 aspects. Number 1, to become a super user, you need to know what data is required. And it's kind of data intensive. You might think of that as a negative of simulation, but it's actually just the way it goes. Data is required, and so for you as a super user, you need to understand what data is needed. Now, the good news is that mixed model line design, the way we teach it, really addresses, I wouldn't say 100%, but 95% of the data requirements are going to be filled through the data collection you would do for a static mixed model line design anyway. So that's very good news. You're not reinventing the wheel or having to go out and gather a lot of different new information. It's already being provided there through that static line design process. So that's good news. Now, the other side of being a super user is, how do you interpret the data in order to use it to improve a process or improve a value stream? Because these software systems can produce a ton of data, and you really need to be trained and educated as to how to read it, how to interpret it, how to look for bottlenecks, for example. How do I analyze simulation output and really identify the bottlenecks in a process or in a value stream? So that's another big part of becoming a super user, is to become a knowledgeable user of the output. And of course, computers can generate a lot of output. The third aspect of it, which I'm suggesting you can contribute to, but you mainly leave to the experts, is the building of the model itself. And that's where typically you're getting into programming. You need to know how to code. Unless the scenario is extremely simple, you very quickly, no matter what software you're using, you very quickly run into the need to write code or macros, those kind of things. And so, and the more complex the system, of course, the greater the need to write code. And they typically have a macro or a scripting language in most of these software packages. So that's where it starts getting complex, and that's where I'm suggesting that I don't want to discourage you from pursuing that, but generally speaking, we have some experts that are going to help build the model itself. So you're going to help as a super user, help on the input and help on the output, and then contribute as you can. But you have a team within your company, or it could be an outside simulationist, outside simulation consultant to build the model itself. And then you're the one actually running the experiments and using it to improve that value stream. So that's what we have in mind. And so we want to make, longer term, we want to help you through this training series, help you to become the super user, valued team member. And we've talked before in terms of becoming line designers and how good that could be for your career in virtually any company. If you can design high-performing processes and you're involved in manufacturing, you are a valuable contributor. You're adding a lot more value to the company than you're costing, basically. And if you add simulation on top of that, just multiply that by a factor of I don't know what, because a really valuable skill to have. So I want to encourage you to be thinking in those terms as well. So I love these stories. You probably do too. I think when you listen to a series like this, you may not remember everything that I've said, but probably you remember some of the stories. So here's a great one. And this was a simulation, not exactly a success story. It's more like a simulation failure story, but hopefully educational. And it's with a company, I guess I can mention their name because they're no longer in existence. They got bought out. So I guess I'm free to use their name. But it was a company you're all familiar with, I'm sure, called Compaq Computer. And Compaq was one of the big PC makers, as you know. And they had their headquarters down in Houston, Texas. And here's the story. And this actually is an actual story that happened when I was working for the Quran Consulting Group in California. The story was this. Compaq was competing in the pretty competitive arena of personal computers, and they wanted to be able to compete more directly with this company called Dell. And Dell had this way of doing things, which was pretty revolutionary at the time and very lean, actually, which was build to order. So you place your order. In those days, it was probably not so much ordering online, but you would pick up the telephone and talk to a rep and place your order for a computer, and you could specify the memory and the hard drive size, which was a lot smaller in those days than we have today. And then they would assemble that computer for you to order. And so they wouldn't be assembling a bunch of generic PCs and then going and modifying them later. They would do it right the first time. They would assemble it to your exact specifications. And Dell was not doing that. Sorry, Dell was doing that. Compaq was not doing that. Compaq was building generic models, and then a third party, not even Compaq, would be modifying these boxes by adding memory or adding a different disk drive, etc. And that was much more inefficient, expensive, and slow compared to what Dell was doing. So they wanted to compete with Dell. And, building to order requires some systems, and that was a big advantage at Dell. It requires order processing, order management, so you know how do you communicate this information down to the factory floor. But assembling a unique model is not that big a deal. But here's one of the big deals they had. Dell, and I don't think Compaq knew this, Dell had put a limit on the order size. So if you wanted to buy 100 computers from Dell, I'm speaking Dell here, you could order 100, but it would be 5 orders. Right, 20 pieces per order. I think I've got that number right. Don't quote me on that. But something like that. So 5 separate orders, meaning they could ship those 5 orders independent of each other. So Compaq didn't have that. So if you ordered 100 computers from Compaq and you wanted them shipped complete, that was 1 order. So what difference does that make? Well, Compaq needed to know, and they were building a whole new building, right, to compete with Dell. They needed to know how much staging space do we need based on our past order history, anticipated future order history. How much staging room do we need? Just physical space. Because if I have an order for 100, guess what? I've got to put 99 computers somewhere until that last one comes off the line so I can ship the 100 as one group. Remember, Dell didn't have that problem. They needed space for smaller number, 20. So they hired not us, they hired an expensive, well-known, internationally known consulting company to do this analysis for them. And the result of this study, done with spreadsheets and Excel, was Compaq, you need 25,000 square feet of floor space for staging. Okay? Now, in the 11th hour, as they're launching this initiative, launching the building project, basically, they said, maybe we need a second opinion on this. This is too important. So they hired Quran Consulting Group in San Diego to build a simulation model. So simulate order arrivals, order sizes, look at past history, and actually give us a more scientific idea of the space needed based on simulation modeling. And so Quran Consulting Group did that, built the model, came back to Compaq and said, here are the results of our efforts. You need 100,000 square feet of space, which was 4 times the space that this other analysis had recommended. So of course, Compaq looked at the two, 25,000, 100,000 and made the rational decision, 25,000 looks a whole lot better. And that's what we were planning on anyway, so that's a good decision. And they went back to Quran Consulting Group and said, I don't know what you guys did, but clearly you screwed up. And the simulation model is wrong. It's got to be wrong. It's so far off from what this highly paid, professional group determined. So we're going to go with the original estimate. Thank you very much. Go away. Don't darken our doors again. So they were a little bit rude about it. So you can imagine what happened, right? 6 months later, when the building's already built, production was already ramping up, Dr. Ali Quran from Quran Consulting Group, the president, got a phone call from Compaq, from the senior vice president of operations. And the phone call went something like this. Dr. Quran, I'm calling you to apologize because we gave you a little bit of a hard time about your 100,000 square foot estimate, and we're now in production, and we found out, unfortunately, we found out that you were right. You were right at to begin with, and it's causing us some issues, and more than a few issues, because as time went on and they started ramping up production, that 25,000 was completely untenable, and they had to start using trailers out in the parking lot, to handle overflow. At some point, it became a total nightmare, and they had to basically cancel that experiment. And because of the opportunity cost in competing with Dell, the estimate has been that was a $300 million mistake of not believing the model. Now, interesting story, right? Now, are models always correct? Obviously not. That's a risk. That was a risk. Simulation's not foolproof, and there could be a risk of believing in simulation too naively, let's say. But in that case, the model was correct. And so you can see here the power of actually modeling before you take action and really kicking the tires on the model rather than simply going with a static calculation. So, true story. So we're still talking about why simulation modeling. So let's continue on that subject. Why is simulation modeling so important? And let's talk about a couple potential objections to doing modeling. One of them, and these are objections we've heard over the years. One of them is it's too difficult. It takes too long. Well, yes. Well, however, consider the alternative, as in the Compaq story. Too difficult and takes too long is all relative. The difficulty and takes too long is all relative to what the options are. If you have to completely abandon your efforts for the moment to compete with Dell Computer in that very competitive marketplace, that's pretty serious. So consider the alternatives and what is the risk. So even if you learn nothing from building a simulation model, no improvements, no change to your original static design, it might be worth it from that point of view, just as an insurance policy. And we've seen that more than once, where a plant manager has said, I'm going to take a part of my investment in this improvement budget, this line redesign, and I'm going to invest it in simulation modeling, not because I think I'm going to learn something new, although we hope we do. I hope we come up with a better design, but simply because we want to make sure that we don't have major mistakes. So I'm treating it as an insurance policy. If you pay for health insurance, you'd like to never have to use it, right? Or car insurance. We pay for car insurance every month. We prefer not to have to use the car insurance because that means you had some kind of accident. So you might think of it that way. Here's another objection that we hear. We're too small and we don't have a simulation department, so we can't really use it. Well, you have a couple choices as a smaller company. One is you can hire outside people. Again, these people are not cheap. They're in demand. Their skills are high, but they are available, right? They exist in the world. So outside simulationists. The other thing is, or another opportunity is you cultivate in-house people that are excited and interested in learning about this. There are training classes. There are online simulation training classes, and there are live classes you can go to. And there are some simulation software packages that are probably easier to learn than others. Let me give you a couple suggestions from what we've seen. Again, we're not getting royalties from recommending this. In fact, I'm not even recommending them. I'm just letting you know that they exist. One of them is called Simulate. I've used Simulate before. It's a 2D system that's pretty user-friendly and kind of graphical. drag and drop, so that's a good choice. ProModel is one of the big simulation companies. They have a very expensive full-blown package, but they also have a version that runs as an add-in to Visio, Microsoft Visio, flowcharting program. So that is something, I haven't used that myself. I'd like to learn more about that, but that's another option. Third one is a product that we do have called iGraphics. Again, it's a flowcharting program, but they have added some simulation capabilities to it. So there's some simpler things you can do internally, right? If you have the right people, the right smarts, and the right enthusiasm for this, you can train them to do this in-house. And of course, I mentioned before, larger companies may have simulation departments that you can tap into. Unfortunately, with these departments, they're also usually pretty busy as well. But those could exist. And then the third objection that we hear often is that software is too expensive. And it is. I won't say too expensive, but it's expensive. It's not like buying a copy of Microsoft Word, right, or a copy of Office. And one of the reasons it's so expensive is it's kind of a specialty. So if you have a software company, a simulation software company, you're probably not going to sell tens of millions of copies because it's a specialty kind of application. And Simulate started out as being kind of an affordable simulation package. I don't know how long ago, a long time ago, maybe 15 years ago or more. They decided to compete on the basis of price and kind of penetrate the market. But I think what they learned was that it's pretty hard to run a software company with all the support and the development, all these things that you need, if you can't sell enough copies to pay for that. So their price has jumped up as well, although I think it's a little more affordable. But the other thing about expense is, yeah, expensive for you as an individual maybe, right? If you want to run out and buy your own copy and play with it at home, but for a company it could be cheap because one improvement could pay for the software in about a day, right? Depending on what you're talking about. So expensive is all relative, and from a company point of view, this could be really cheap, a really cheap investment, depending on the opportunities that are there. So these are three common kind of objections. There are a lot more. The biggest one, though, I think is just the learning curve part of it. And as I said, in lesson 2 of this series, we have some solutions to that will be, I just want to give you a little teaser now, but we'll be sharing with you one way to kind of get around that. So in this series, in this introductory lesson, we've talked about the why simulation is so important. And we'll probably leave it at that. Hopefully you're intrigued, if not excited about it. And in the next lesson, we'll talk about the what. So we'll be sharing with you some actual examples of how you might do this, how you might be using, again, with actual screenshots, actual demonstrations, how you might be using a simulation to improve mixed model line design. So look for this second email. It'll be sent to you in a couple days. And we'll look forward to continuing our discussion during that one. One last thing, what I'd like you to do, add your comments to this page. If you have any, you liked it, didn't like it, good start. I have these questions or challenges. Post them all on this page, and we'll make sure we take a look at those and try to address them in the upcoming lessons. So remember, look for lesson 2 in just a couple days, and we'll see you then.